All right, pre-calc students, welcome to lesson 2 of the probability unit. Our focus for this lesson is going to be on combined events. Combined events, essentially, when we talk about combined events, we're talking about conditional probabilities. And when we are talking about conditional probabilities, this includes conversations about whether or not events are independent or not, or mutually exclusive or not, and we'll also touch on some strategies you should be using as you approach questions, as well as different ways to define sample space like tree diagrams or Venn diagrams. In an effort to keep the video as succinct as possible, I'm only going to do selected examples that highlight the key conceptual ideas for the lesson, and then at the end of the video I'll put up the worked solutions for all of the examples that I'm going to skip over. And so to begin with, I'm going to skip over the warm-up that relates to stuff from lesson number 1. Okay, and so first we're going to address this idea of simple probability, simple theoretical probability, which is just the idea of counting the number of events that are desired divided by the total number of possibilities. And so we go straight to example 1. We have a letter to be selected at random from the letters in the word Tampines, and we want the likelihood that the letter is a consonant. And so all we need to do here is figure out how many consonants we have and how many letters we have in total. And in this case, it's simply 5 consonants out of a total of 8 letters. The probability that the letter is not a consonant, we could of course approach this in the same way, but we want to attempt to start thinking about this notion of complementary events. The probability that something is not is 1 minus the probability that it is. And so we can use our previous answer to get the correct answer of 3/8. Of course, in this case, it's very easy to just count the number of vowels, but conceptually the idea of a complement is important. All right, and then last but not least, what is the probability that the letter is a T or an S? And again, that just involves counting the number, 1 T and 1 S, out of a total of 8, and there is no expectation that you give your answer in simplified form, and so we would of course accept 2/8 as a correct answer. Okay, now we're going to move to this the beginning notions of independent versus dependent events, and specifically we're going to give a definition for something known as conditional probability, and this is the notion that the one event is affected by whether or not another event has occurred. And so if the probability of an event depends on whether or not A has occurred, then those events will be dependent on each other. This notation reads the probability that B occurs given that A has occurred. And essentially what you need to understand with conditional probability is once something is given, ultimately what we've done is we've altered the sample space. And so instead of having all the different possibilities, what we do is we limit the sample space. And so as a quick for instance, if I said what is the probability of selecting I given that we selected a vowel, then the given event means that I've limited my sample space from 8 to 3 because I told you it was given that it was a vowel, and then how many of the options were a desired outcome over the total number. And the key here to understand is that the total number is altered because there is an event that's given. So sample space is altered or typically reduced. All right, and so here's our definition. Will be given on the theorem sheet, so no need to memorize. It's just a key, as always, to conceptually understand. So probability of B given A is the probability that both A and B occur divided by the probability of A occurring, which is the given event and is the limited sample space. All right, so let's do an example. This one specifically prescribes a tree diagram, which is one of our ways of being able to model sample space. Okay, so we've got 3 yellow blocks, 7 green blocks. two blocks are being drawn, and of course the key here is that it is without replacement, and so the probabilities of the second draw are affected by whatever is chosen on the first draw. Okay, and so two blocks are being randomly drawn, and so what we have in the first instance is I either get a yellow block or I'm going to get a green block. The chance that I get a yellow block is there are 3 yellow blocks out of a total of 10. Of course, you can write that as 0.3. Chance that I get a green, 7 green blocks out of a possible 10. And then on the second draw, the outcomes are the same. It's either yellow or green, but following different outcomes from the first draw. And so in this case, to draw yellow on the second one, there are now 2 yellows left, and the sample space is now 9. So we only have 9 blocks left because it was without replacement. There's still 7 green blocks left, but total of 9. If I drew green on the first, then for yellows, those are unchanged. And for greens, I would have had 6 out of 9. So here's my tree diagram that represents my entire sample space. And then just a reminder, generally speaking, we multiply along the branches of a tree diagram and we add across the branches of a tree diagram. And I'll explain what I mean by that as we get through a couple of the examples. Okay, so let's start example 2b, probability that neither block is green. There's a few different ways of expressing this. This is, of course, the same thing as the probability of drawing yellow followed by yellow. And so again, if I want yellow and yellow, I'm moving along the branches, and so that's going to be 3/10 multiplied by 2/9, 6 over 90, which you can simplify or not. It's not a requirement. All right, probability 1 block is green and 1 block is yellow. And so in this case, you want to be aware of the fact that if we've got a yellow and a green, there are 2 different ways that this can happen. We could also get green first and yellow on the second. And so this is the example of multiplying along and adding across. And so in this case, I'm going to say probability of green yellow, or it's the probability of yellow green. And so in this case, we're going to get 0.3 or 3 over 10, which is yellow first followed by green, or and so that's our general rule, or implies addition, or we're going to get green first and yellow second. And so we're going to get 42 out of 90, 7 3s 21, and we are adding and subtracting. Common denominators already 90. Okay, so here's our symbol for given. So what is the probability that the first block is yellow given that the second block is green? And so I'm going to start by just writing out the formula. And so my formula would be the probability of yellow on the first draw and green on the second, divided by the probability of the given event. And so the probability on the given event is that we're going to get green on the second. And so I'll just highlight green on the second can occur in 2 different ways. And so that's going to be our denominator. And our numerator, probability of yellow on the first followed by green on the second. And so we have 3/10 multiplied by 7/9, and that's going to give us our probability of yellow first, green second. And then probability of green second is going to be 3/10 times 7/9 plus, so we've got the yellow green, or we've got green green, which is also a way of getting green on the second. And so that's going to be 7/10 multiplied by 6/9. What you cannot do, 2 things that you definitely don't want to do. The first thing that you do not want to do is to cancel these and these, because you are cancelling across a plus, and of course you are not allowed to cancel across addition or subtraction. and so we definitely don't want to do that. And let's move on to here. And the second thing you don't want to do is leave your answer in this form. While we don't require simplifying, we do require that you complete the operations, and so in this case we do need to add and subtract our fractions, and not leave it as a fraction over a fraction. And so we're going to do a little bit of cleaning up. This is going to give us 21 over 90. Our denominator is going to give us 63 over 90, and when I divide a fraction by a fraction, multiply by the reciprocal, I'm going to get 21 over 63, which you can simplify or not. Alright, moving on to example 3. And so what's key to understand with example 3 is that conceptually it's the same idea, exactly the same idea as example 2. We've got selections from a jar or a box, and those selections are without replacement, and so conceptually it's the exact same idea. The difference here though is we are selecting 5 blocks, and so if you were to try to do this problem using a tree diagram, adding 2 branches for each of the events, you are going to be dealing with a tree diagram that has 32 branches in the end. And so the key here is to make the transition essentially from algebra 2 to pre-calc, where we've got to realize the strategy for approaching this problem should be combinations or combinatorial numbers. And so combinations are going to be the way that we're going to deal with this, because the tree diagram becomes impractical. Okay, and so what is the probability? So a very similar question, 12 yellow blocks, 8 green blocks, and we are drawing 5 without replacement. And so the probability that none of the blocks are green is essentially the probability of 5 yellows. And the way we can draw 5 yellow blocks is 12 choose 5 is going to be our 5 yellow, divided by the total number of ways of choosing 5 blocks out of 20. And of course we're not being asked for the total number of ways, we're being asked for probability, and hence the need for our denominator. Okay, also keep in mind that when we're talking about combinations, combinatorial numbers, we are talking about instances where order does not matter. Okay, and so this is different from permutations where order does matter. In this case, we're just asking for different combinations and we don't care in what order we get them. All right, part B, example 3b, what's the likelihood, which is essentially another way of saying what's the probability. 2 of the blocks are green, 3 of the blocks are yellow, and again the order in which that happens does not matter, and so we're looking for probability of 2 green and 3 yellow. And so in this particular case what we've got is out of the 12 yellow blocks we need to select 2. So we have yellow, I beg your pardon, 3 yellows, my apologies. So 12 choose 3, and generally speaking that's multiplication, and out of the 8 green blocks I need to choose 2, and my denominator 20 choose 5. Again, I'm still selecting 5 blocks. Generally speaking, we're going to allow you to leave your answer like that in combinatorial form. There will be an explicit instruction on the quiz and the test telling you when you can do this and when you cannot. Okay, and we then move to a question which is going to involve conditional probability. And so given that all of the blocks are the same color, what is the probability that all of the blocks are yellow? And so always pay attention in these questions. All of the blocks are yellow is in fact the answer to part A, and so we already have part of the solution and let's go back and work on essentially what we need to do is probability of 5 yellow given that they were the same color. Alright, and so if I interpret that same color means we had 5 yellows or we had 5 greens, and that's the part where you have to be a little bit careful. So we know that the number of ways to get 5 yellows is 12 choose 5, and the way to get 5 yellows or 5 greens, 12 choose 5, or in the other option to get all the same color is of course 8 choose 5. So that would be 5 yellows or 5 greens, and again we can leave our answer like that. We do not want to do any cancelling because you cannot cancel across a plus sign. Okay, moving on, we now go to again essentially a combinatorial number question again. This involves a standard deck of 52 cards, and so we're just going to go through this one. It's a combinatorial number question, but it's got a couple of elements which are a little different, which is why I'm going to deal with this example, even though it is very similar to example 3. Okay, so we've got 5 cards that are drawn, total sample space or total number of options 52 cards, and we want probabilities of all hearts. And so there are 4 suits in a deck of cards. Hearts are 1/4 of the cards, and so there are going to be 13 hearts in a deck, and so it's 13 choose 5 divided by 52 choose 5, the way total number of ways of getting 5 cards from a standard deck of 52. Exactly 2 hearts. Now we want to watch out for the word exactly. That means no more and no less. And so in order to get 2 hearts, that means we need 13 choose 2, and that means out of the remaining cards, of which there are 39, the remaining 3 cards must come from the 39 that are not hearts, and our denominator in this case remains the same. Okay, part C, exactly 1 diamond, 2 hearts, and the queen of spades. And so same thing again, I'm going to start off and deal with my denominator this time first because that's unchanged. And so if we want 1 diamond, in the same way, that's just one of our suits, and so there's going to be 13 of them, and so that's going to be 13 choose 1, and out of the 13 hearts we are choosing 2. Out of the 1 queen of spades we are choosing 1. Of course you could have just put down the numerical value 1. 1 choose 1 is going to produce the numerical value 1. And then finally we need the remaining cards, and so there are 25 cards remaining in the deck. Alright, 13 and 13 is 26, and 1 is 27, plus 25 gives us our 52, and we need the final card to come from the remaining 25. Okay, and that's our probability over there. Next example again is still combinatorial numbers, but what we're dealing with here is just the language, at least 1 club. And so this is the example where we want to think about the notion of a complement, because at least 1 club means 1 or 2 or 3 or 4 or 5, and that's us representing 5 different possibilities, which is time consuming, and it's going to burn your time. There's a much faster way to get to the answer, which is to say 1 minus the probability of no clubs, and that will take care of all the different possibilities. And so this is the value of using the complement. And so I'll just scroll back up really quickly. That's this idea of a complement, which we used in example 1b in a very simplistic way, but here you can see an example a little more complicated where we want to save ourselves a lot of time. And so in this case the probability of no clubs is that we choose all 5 of our cards from the 39 cards which are not clubs, and of course since we're dealing with probability, we must account for the denominator, total number of combinations of 5 cards from 52. Okay, I'm going to skip over example 5, very much the same kind of example as we've done before. The question is simply asking about whether or not we should use combinations or a tree diagram, and in this case the answer to that is we're going to be using a tree diagram, and the reason for that is we've got a multi-stage event here. And so you'll notice we've got a fair-sided die is tossed, and then a marble is selected from a bag. And so in this case, the key here will be to use a tree diagram, which is really amenable to representing multi-stage events. All right, let's move to the next key idea, this notion of independent and mutually exclusive events. And so really important to understand that whether something is independent or not doesn't always necessarily dictate whether something is mutually exclusive or not. And so these are separate conceptual ideas, and you need to not think of them as being related. They have their own separate approach. Okay, so here we have one of your probability rules, which is on your theorem sheet. So the probability of A union or B is going to be A's probability plus B's probability minus our probability of A intersection, or A and B, which is the standard probability for events, combined events. And what we need to do now is look specifically at our two separate ideas of independence and mutually exclusive. So first things first, I think you've got a small typo in your note. It's missing probability of B in your little formula at the bottom there. So please just make that edit now. And so let me talk really quickly about this. So if events are independent, what it basically means is that the occurrence of one event does not affect the outcome of the other. For instance, the tossing of a coin, the rolling of a dice. And so if I roll 5 sixes in a row, and on the sixth roll of the dice I'm wanting to know what the probability of getting a 6 is, that remains 1/6 because that's an independent event. It is unaffected by what has happened prior to that time. Mutually exclusive events are events that cannot occur simultaneously. And so, for instance, I roll a dice, the probability that I get a number that is both odd and even. Once something is odd, it cannot be even. And so that's an example of something that is mutually exclusive. Visually, what you'll see is that your intersection of the two events will be 0. There will be no overlap because the events cannot occur simultaneously. All right. And so what we're going to do here is take care of a Venn diagram question, which will then also be used to highlight this notion of mutually exclusive and this notion of independent events. All right. So we've got a total of 350 students surveyed on language classes. 150 took Spanish, 205 took Mandarin, 25 took neither. And so what we're going to do is we're going to start with the students who took neither and fill them into our Venn diagram. And then we need to essentially figure out, our next stage is to figure out how many of our students took both Spanish and Mandarin. And the way we're going to do this is to say we've got a total of 350 students. And if we were to take away the 25 that took neither, take away 150 and take away 205, we're going to get an answer of minus 30, which of course we realize is not possible. And so what that indicates is that there were 30 students who doubled up on Spanish and Mandarin. Okay, then we can go back and say, well, if 150 students took Spanish, that means 120 took only Spanish and the 30 came from the group that doubled up. Similarly, 205 took Mandarin. If I deduct the 30, I'm going to get 175. And now if I add the numbers in my Venn diagram, they total 350, which they should, because the Venn diagram is representing the total sample space, which in our case consists of 350. Once we have our Venn diagram completed, the rest should be relatively quick and easy. And so probability of Mandarin intersection or and Spanish, we've got 30 students out of our total of 350. The probability that a student did not take Spanish is going to be everybody who took only Mandarin, as well as those who took neither Spanish nor Mandarin. And so that's going to be 175 plus 25 over 350. and so we would expect you to take that one additional step of completing operations, but then you can leave your answer in unsimplified form. Probability of either Spanish or Mandarin, and so the union of those two is going to be the complement, 1 minus those who took either Spanish or Mandarin or both, and in this case we can really easily say it's 350 minus the 25 who took neither, or of course we can just add up the values, and so we're going to get 325 out of 350, and then our conditional probability question, and nothing unique about a Venn diagram. Actually, dealing with conditional probability in a Venn diagram is really easy. We've got the given event, and so all we need to do is only consider those elements, and so let me just change that color so it's a little more obvious. We're only considering the elements inside the given event, so we've limited our sample space, and so immediately we know that we're dealing with a reduced sample size. So out of the 150 students who took Spanish, how many of them took Mandarin? And in this case it's the ones who doubled up, 30 out of 150. Okay, now we deal with the two big conceptual ideas for the lesson, and so are taking Mandarin and taking Spanish mutually exclusive events? And so in this case, given that the probability of Mandarin and Spanish equals 30 out of 350, which does not equal 0, we can conclude that the events are not mutually exclusive because we have students who doubled up, and so the events can occur simultaneously, which means they are not mutually exclusive. We would expect you to show evidence of working and then evidence of reasoning, which would be your conclusion. Okay, and next we're looking at the probability, not the probability, determining whether or not taking Mandarin and taking Spanish are independent events. So does taking of one of the languages affect the likelihood of taking the other one? There are two different approaches that we can use in this case. One would be to consider whether the probability of taking Mandarin and Spanish is equal to the probability of taking Mandarin multiplied by the probability of taking Spanish. And so if this is the case, then that proves that they are in fact independent. And so I'll come back over here to prove independence. If probability of A and B is just the product of the two of them, then that proves independence. The other way that you can prove independence is to show that the probability of taking one of the languages, so let's say Mandarin given Spanish, and so I'm picking that one just because we've already got the numerical value we've got the answer. And so if the probability of taking Mandarin given Spanish is the same as the probability of taking Mandarin, then that's another way to show whether or not events are independent, because in this case, if taking Mandarin, the chance of taking Mandarin is unaltered by whether or not you took Spanish, then that highlights that the events are independent or not. And so either one of these methods will suffice. And so now we're just going to fill in some working. So we've already got our numerical values, or most of the numerical values that we need. So probability of Mandarin and Spanish we figured out from the first question, 30 over 350, and what we're trying to figure out is whether or not that is equal to probability of Mandarin, which we can read off the Venn diagram. There's 205 out of 350 multiplied by probability of taking Spanish, which is 150 over 350, and then we can determine that those are not equal to each other, and therefore the events are not independent. The alternate approach would be to use the given events, and so probability of Mandarin given Spanish is 30 out of 150. Probability of taking Mandarin is 205 out of 350, And so in this case, once again, those are not equal to each other, and we would draw the same conclusion but using the alternate approach. Okay, and so there's a couple more questions for us to take a quick look at. And so what I'm going to do in this particular case is I'm just going to deal with example 7 as the last one. And like I mentioned before, we've got some examples which are going to be somewhat repetitive. And so I'll show the worked solutions for those right after example 7, but you should be able to handle those yourselves. What I would encourage you to do is all of the examples, including the warm-up that I've skipped over, I would suggest that you work those before looking at the solutions to see to what extent you've managed to understand. Okay, so last one. This question is just asking about mutually exclusive, and it's also asking about independence, but the difference here is the information is given in a slightly different form. You could attempt to incorporate this into a Venn diagram. It is possible. In this particular case, though, in the interest of time, I'm not going to do that. I'm just going to go straight ahead and do the calculation. So probability that the events, or determining whether or not the events are mutually exclusive. And so I'm going to go back here just really quickly. The formula I'm going to use is the probability of A or B. And so I'm going to work out probability of A or B is going to be the probability of A plus the probability of B, beg pardon, sorry, minus the probability of A and B. So that's the formula that I'm using, and then I'm just going to go back in and replace A or B with 3/4, and I'm going to work out that the probability of A and B in this case is going to produce the numerical value of 1/12. That of course does not equal 0, and therefore my conclusion is that they are not mutually exclusive, because I've shown that there is an overlap. And similarly, we've got the probability of A and B, or A intersection B, from the first part is 1/12. I'm going to work out that the probability of A times the probability of B is 1/2 times 1/3, which is 1/6, which does not equal 1/12, and therefore I can also conclude that these two events are not independent. Okay, so a few more examples for you to use to check your understanding. At this point, I'm going to just really briefly scroll through the worked solutions for those, and that way it'll allow you to check. Of course, you could also have a look on Google Drive. And so here are solutions to the warm-up. There's example 2 and 3, which we took care of. Example 5, so there's our multi-stage event. The solutions to our multi-stage event using our tree diagram. And then we have got example number 8. Again, it's effectively done with a tree diagram. And last but not least, our combinatorial number example